Welcome to The Explainer. I'm absolutely thrilled to have you here today because we're going to unpack a topic that's as massive as it is completely invisible. Let's start with a classic analogy, right? The iceberg. When we're talking about multi-million-dollar dredging and subaqueous excavation projects, the biggest financial risks aren't those giant cranes or the massive ships you see on the surface. No way. The real risks are completely hidden below the water surface. We're going to dive into the hidden geometry of the ocean floor and explore a crazy story of how the way we measure it dictates millions of dollars in final infrastructure costs.
So let's just get right into it. Industry expert J.A. Ciartino really hit the nail on the head when he said accurate volume estimates are important for the choice of dredging plant, production estimates, and ultimately project costs. You see, in the dredging industry, calculating geometric volume is quite literally the exact same thing as calculating money. Every single cubic yard of sediment that gets miscalculated, that's a potential budget disaster just waiting to happen.
Which brings us to this incredibly fascinating, kind of mind-bending question. How do you measure a mountain of dirt that is totally hidden underwater? That's the core mystery of subaqueous excavation. When you're measuring an invisible, highly dynamic environment, you're inherently creating massive contract compliance risks before a single contract is even signed. I mean, you can't exactly just walk out there with a tape measure.
Well, the first major hurdle we hit is simply time. There's a temporal lag, usually anywhere from 6 to 24 months between the initial hydrographic survey and the actual physical excavation. And as we know, nature never stops moving. During that long waiting period, coastal storms, changing tides, and natural sediment transport are constantly altering the bottom topography. So, months before a shovel even hits the water, the blueprint is literally shifting while you're holding it. For a long time, engineers tried to measure this moving target using something called the average end area, or AEA method. It relies on really sparse data, taking these horizontally projected cross-sections of the seafloor spaced anywhere from 100 to 500 feet apart. The mathematical formula then just basically assumes that the ocean floor is a perfectly uniform straight line between those distant points. Spoiler alert, the ocean floor is almost never a straight line.
So, the crucial question is, what happens when you use flat math on sloped underwater terrain? Well, because the average end area method uses average dimensions for what are very often sloped excavations, it mathematically creates a systematic volume underestimation of roughly 11.5%. Just think about that scale for a second. That is a massive chunk of missing data and missing money, all because the formula inherently struggles with slopes.
We call these issues geometric blind spots, and they create some major real-world distortions. For example, in the sweep of a curved channel, AAA completely fails to account for the space between the survey lines. And even wilder, if the bottom suddenly drops below the design level, the math calculates a flat zero for a space that's actually filled with water and mud. It just doesn't compute.
It's what we call the flaw of averages. It's a total geometric illusion created by forcing 2D math into a complex 3D world. And when the mathematics completely miss these unsampled peaks and dips, it creates enormous financial liability and massive cost overruns for the dredging contractor. They end up bidding on and getting paid based on a totally incomplete picture of the seafloor. But enter the modern technological game changer, the triangulated irregular network, or the TIN method for short. Instead of taking flat, distant cross-sections, TIN is a vertical projection method that models the entire surface as this continuous, connected fabric of small triangular planes. It uses high-density multi-beam echo sounder sweeps to capture the true exact position of every single depth sounding. It's like throwing a digital net over the entire ocean floor. And when you benchmark the data, wow, the results really speak for themselves. While the old AEA methods hover around a 1% error rate, regardless of how closely spaced you make those cross-sections, by the way, the TIN method cuts that geometric error rate in half. It brings the error down to less than 0.5% compared to the mathematical baseline. That is a huge upgrade. Let's quickly walk through the logic of how TIN actually solves these geometric blind spots, because it's super elegant. First, the software generates a triangular mesh with break lines so it doesn't accidentally cross physical boundaries. Second, it extracts exact x, y, and z coordinates. Third, it computes the vertical elevation differences. Fourth, it calculates the horizontal projection area. And finally, it sums up all those individual prismoidal volumes. Basically, it treats the channel floor like a true 3D grid of connected prisms, rather than a bunch of disconnected flat slices.
So why does all this complex modeling actually matter to the bottom line? Simple, because precision pays off. These high-density 3D models completely eliminate those nasty curvature biases inherent in the old methods. By tying these 3D models to local tide gauges and shoreline temporary benchmarks, modern surveyors can achieve an incredibly tight survey accuracy of plus or minus 0.5 feet in sheltered water. Half a foot. That is just stunning precision for an underwater environment you can't even see.
Okay, but here is where our story takes a really fascinating turn. Measuring that in-situ geometry on the ocean floor, that's actually only half the battle. Even if you have absolutely perfect 3D math and incredible survey accuracy, the physical reality of the dirt itself changes the exact second the dredge begins to dig. This brings us to a really cool geotechnical phenomenon known as the bulking factor. When you excavate soil, it undergoes disaggregation. Basically, it breaks apart. It loses all that natural compaction that took centuries to form, and it experiences massive water entrainment. Because the soil physically expands when it's excavated, the perfect volume you just measured on the ocean floor is vastly different from the bloated, wet volume now sitting in your transport scow.
So how on earth do you fairly track this expanded, wet material? Well, the outdated way relied on visually reading manual draft marks on the side of the boat. But that method grossly overestimates the volume, because it captures all the pooled water inside the hopper as if it were paid sediment. Today, thankfully, the industry is moving toward automated dredge quality management, or DQM systems. These bad boys use high-tech sensors combining hydrostatic displacement with acoustic ullage sensors, which literally use sound waves to measure the empty space in the hold, all to calculate the true mass of the sediment.
The absolutely crucial metric we get here is called tons dry solids, or TDS. These automated DQM systems are total lifesavers because they calculate TDS, effectively stripping the water weight right out of the equation. By calculating just the dry mass, contractors ensure they only get paid for the dirt they actually moved. And on the flip side, project owners aren't footing a massive bill for simply moving ocean water from one place to another. Win-win, right?
This entire journey perfectly highlights why we should care so much about these measurements. From the unseen ocean floor all the way to the final project invoice, geometry dictates the financial reality of our infrastructure. The story of survey data isn't just about making neat, high-tech maps. It's a story of how the mathematical models we choose directly dictate final dredging cost estimates and, ultimately, the success of massive global infrastructure projects.
Which leaves us with this final, somewhat provocative thought to ponder. If high-density 3D models and advanced automated sensors solve our geometric blind spots, will they finally eliminate dredging cost overruns for good? Or will peering this closely into the hidden depths just reveal entirely new, hidden complexities waiting for us down in the mud? Thanks so much for learning with me today, and keep questioning what's beneath the surface.